Buenas tardes, colegas Cima Sur, buenas tardes a los que están en YouTube. Hoy día tenemos nuestra segunda charla del ciclo de Cima Sur, que vamos a continuar en enero, desde el lunes y después en enero. Tenemos a Irina, no voy a pronunciar tu apellido porque me pidió expresamente que no lo pronuncie, que es actualmente nacióloga libre de CIASA, trabaja también en la Universidad Tecnológica de Ciencia y Tecnología de Noruega, en TNU, tiene un grado universitario en matemáticas, un doctorado en computación y experiencia doctoral y postdoctoral en biofísica. Y trabaja en temas de glaciología, climatología y geografía física. Tiene varios sitios de trabajo, ahora está en Lausanne, está trabajando en Europa, en el Ártico, en la cordillera norteamericana, etc. Y hoy día lo que nos va a presentar es como un popurrí de las cosas que está trabajando en diferentes escalas de espacio-temporal. Y bueno, súper excited de tenerte aquí, poder escucharte. Generalmente las charlas son así, entre online y persona, y tengo aquí las personas aquí conectadas. Así que eso, muchas gracias Irina, y te dejo adelante.
So it will be a bit of a practice of English today because the talk will be in English.
No worries.
Right? Yeah. But could you please check with the audience if they can hear when you are speaking in this direction? Could they hear the microphone?
Just talk, I can hear you.
Okay, so I'll walk around with the microphone. I don't remember where the pointer is.
I can hear the pointer.
Yeah, but in general, I prefer to maybe not touch the screen and use the pen.
That's, I think it's,
yeah. Okay. Yeah. So, Irina Rogozhina. I'm Russian, right? My husband, in 17 years of marriage, hasn't learned how to pronounce my name. That's why I prefer, and he's Chilean, Rogozhina. I mean, it's not easy for foreigners. In Germany, in Norway, everywhere, they had problems with pronouncing my family name. So I just save your time on this, right? Yeah, as mentioned, I have a dual appointment right now as a leader of the glaciology group at CIASA, starting from this year, and as an associate professor in Norway. This is the largest university in Norway in general, even though Norway is quite small. It's only 5 million people. But so basically, today I'm going to walk you a bit through the path of my academic training to introduce into all the different subjects my team is working with. And this I will do with a central focus on ice masses, which have been persistent subjects of my research since 2009. And I will look at this as, I don't know, okay, but it's not visible really, yeah? Okay, I'll just use it like this. As a bridge between atmosphere, ocean, and solid earth processes, and also across different timescales from paleo to instrumental. I'm not so much into science fiction, so the future is still something that I am trying to integrate, but I try to focus on more solid timescales. So I will be presenting these different subjects of research of my team through a bit of an egocentristic approach, how I actually landed at CIASA or on this dual appointment in physical geography, which I have never studied in my life. I'm a professor in physical geography and also a leader of glaciology team. I have been working with the observational glaciology for 5 years only. I never did anything. I never even saw any glaciers before that. So that's a very interesting thing. And today, the main subject of my team is to observe and understand changes in glaciers and permafrost as well, so like rock glaciers, and estimate the impacts of these changes on fresh water, specifically in semi-arid regions of Chile. So very far away from where I started. I started with diploma studies at Moscow State University in applied maths and computer sciences with the major on pattern recognition. And my thesis was actually focusing on the use of machine learning approaches to interpret medical data. So nothing to do with glaciers or even earth sciences. Then I got immediately, like when I was finishing the diploma, I got an offer of a PhD in Potsdam in Germany. Also, I joined appointment at GFZ Potsdam and Berlin Technical University. And I moved a bit closer to what we are doing today, focusing on geodynamics. So at least it's already about the planet. So the PhD thesis basically was around development of a new spectral model of mantle convection and Earth structure with complex rheology. This is where we connected with all the solid Earth people at some point, right? And then this was basically constrained by various surface observations like gravity, dynamic geoid, plate velocities, right? Okay, after maternity leave, I actually started or came back to GFZ Potsdam and switched my subject again to ice sheet modeling. So the main subject was to work on reconstructions of the internal state and changes in present day ice sheets. And in parallel, I have been working there for 7 years, right? In parallel, I initiated two main directions of research where I started connecting different fields. So I went into paleoglaciology. I connected to a huge network, international network, and immediately started leading big projects or like work packages. And then I started connecting my own research across solid Earth ice sheet interactions. And already in 2013, I became a leader of a glaciology group, which was a very junior group. So let's summarize: machine learning, geodynamics, computational glaciology. From there, we start branching out, and I will just have some highlights of different projects for you so that you understand a bit better. So my main role during this time was to lead the junior group and study how ice sheets interact with atmosphere, solid Earth, and oceans. But then in parallel, I started studying the influence of geothermal flux on dynamics of ice sheets and went into paleoglaciology, where I was leading numerical modeling and the use of it to interpret geological evidence, like I will explain later. So we will look now at the highlights for each of the subjects, because my team is still continues working with all of them. And one of the biggest things, the themes in our research has been focusing on the Antarctic ice sheet. I don't think I need to give a big overview of what the Antarctic ice sheet is, but let's just get some important points out. The largest ice sheet today consists of two major ice sheets, one very vulnerable and grounded up to 2,000 meters below the sea level. And it has 5 meters of sea level equivalent, so how much the sea level will rise if it melts completely. And then the other one, much bigger, it has more than 10 times the same amount of water, right? East Antarctic ice sheet that is believed to be stable and not too vulnerable. But this opinion is actually gradually changing. So this whole thing contains about 61% of all fresh water on Earth, and what we're observing today, the East Antarctic ice sheet is still a bit gaining mass because there is more precipitation, while the West Antarctic ice sheet is losing mass very quickly. But it's very important to pay attention to actually what sources are contributing to the loss of this mass. And it's very unique for Antarctica. 45% of mass per year is lost due to ice calving. I'll quickly explain it. I think you know what it is, but still, I'll give a bit of theory. Then we have 55%, much more than this, lost due to ice shelf melting. And I will explain this too. And even less than 1% is lost because of the warming of the atmosphere. So, or in general, there is not so much melting in this region. It's very cold. Quickly, what the ice sheet consists of. And this is not only for this ice sheet, it's pretty much for all ice sheets, usually. So there are three main areas that we need to understand. One is the grounded sector. This is the sector of the ice sheet grounded on solid earth, right? And most of East Antarctic ice sheet consists of this type of ice sheet, right? Then we have floating ice sectors. These are ice shelves. And here you have some examples. These are very big ice shelves. They are not grounded, they're floating on the ocean, but they're still part of the ice sheet. And they're connected through the grounding line, which is a very important factor in Antarctica today. So it's a boundary between grounded ice and floating ice. So this is where it just gets afloat. And all the most important processes today where we are losing ice are happening exactly in this area. There are these two major sources of loss, and we have to look a bit into them. Like you saw these big ice shelves. What happens is that warm ocean water is entering below these ice shelves and melt them, producing fresh water. And then this fresh water is separate from salty water. And it floats a bit as a film, and then it can get refrozen. So my team is developing models that can capture those processes because they're very small scale. No models can handle them. And this is one of the examples. It's my first Chilean PhD student, also postdoc, Jorge Bernales, who actually is developing these models with us. You can see this map here reconstructing basal melt regime in Antarctica. And you can see some very red areas. This is where we lose more than 5 meters of ice per year due to melting from below. But then we also have some blue areas where actually this film of fresh water gets refrozen back to the ice shelves. It's very complex. And our models are too simplistic today to actually capture this. So we are kind of trying to pioneer these developments, but of course there is quite a lot of development going on around the world as well. Okay, then the second process is even worse because models are using very simplistic assumptions about how calving is happening. It's a very complex process. There are the process of formation of cracks even before the ice gets afloat, right? And there are these crevasses. You probably heard about people or professors falling into crevasses. These are the crevasses that then are part of ice shelves, the holes, very deep. And all of this contributes to the presence of weaknesses in the ice shelves. And then under tides, sometimes tsunami, sometimes other processes, we lose parts of this ice shelf. And this is ice calving, and then you have these ice shelves passing by New Zealand. You probably heard about this. So here you see a very complex picture. I don't want you to look at it like in detail, but you can see that black part of the circle shows the contribution of melting of ice shelves from below, while this hedged part, it's calving. So you see very different picture in different sectors of Antarctica. Here in West Antarctica, where the changes are very fast, we have much more contribution of melting from below than calving. But it's very different in East Antarctica, where we have mostly calving and less melting, right? So it's a very complex picture, and that's why one very big task that my team is doing, we are developing models that are better than what we have today, to be able to capture these kind of events. You probably heard about Larsen ice shelves. This is where we are going with hopefully with the expedition now from Chile. It's one of our targets. The Larsen A is not even part of this picture because it collapsed in 1994. But then it keeps collapsing in 2000. Sorry, it was animation, but since I produced a PDF, it's not working. But anyway, in 2002, we lost this part of ice shelf. And then in 2017, also Larsen C is gone. So it keeps collapsing, and we have a lot of smaller ice shelves left. But when the ice shelf collapses, then ice accelerates and is lost more and more in the ocean, right? So basically, this is an unstoppable process. Okay, let's just highlight for what we have been doing all these years, for 10 years already, developing models. Now, that's the subject we have been working on with Andres in particular, right? The influence of geothermal flux on dynamics of ice sheets, and we continue with it until today. Let's look at the other ice sheet that we have today on this planet. The second largest ice mass, it contains about 7 to 8% of fresh water on our planet, and it would raise the sea level by 7 meters or even more, and it's losing mass very fast. So there is a big difference with what is happening in Antarctica. Here we are losing mass, but due to different processes. So primary sources of mass loss in Greenland are about 50% due to both calving and melting of ice shelves, but the rest, 50%, is due to surface melting because of warming, right? So it's a very fast process, and here mass loss is much bigger than mass gain. Let's look at what this means, but from a different perspective than you think. So there is a huge community of ice core scientists. I mean, these are huge expeditions focusing on drilling deep ice cores in ice sheets in Antarctica and Greenland, and they focus on reconstructing long-term history. They want to understand what has happened over thousands, tens of thousands of years. And this is the very first ice core that was drilled as a collaboration with the US Army, but there are many I will show to you. And then, like these are very important records because they're showing to us what was happening during the previous warm periods of the past. But this can also be combined with ice penetrating radar measurements. Here there is a plane collecting the data, and then you can map the whole interior of the ice sheet. I don't know why it got so dark. Yeah, but you can just extend these ice cores and say, okay, here we have 2,000 years old ice, and here it's 90,000. And then you can plan where you can drill, maybe, as we will see, not very successfully, by mapping these layers. These are the most recent 11,000 years. Then below we see the last glacial period, almost 100,000 years. And then we have fragments, remaining fragments of this, the golden age, the period when it was warmer on our planet than today. And the West Antarctic ice sheet collapsed during this period, right? So we want to understand what actually was happening in the northern hemisphere too, but without success. So these two ice cores were drilled. They were very disturbed. We couldn't go into this period. It's not trustable. And then they planned this really expensive project NGRIP, drilling to the base, right? And unfortunately, so here you see records from Antarctica, the blue one. They're very long. They're going really like 800,000 years back, this one. And then we have NGRIP, this really expensive project. They drilled, and then they realized actually the ice sheet was melting from below. It ate all this golden record through the melting. Are you following? Good. Yeah. That was very unfortunate because, of course, who can justify such an investment? And the purpose was not reached. Besides, in addition to this discovery, there were some ice penetrating radar measurements performed, and they figured out that actually the melting was happening over huge areas. This one, the white, is marking areas where there is melting at the base of an ice sheet, this ice sheet. And these are hypothetical rivers that exist there. Okay, so that's from our model actually. How did we get there and what does it mean? Yeah, early research has suggested that there was a very high geothermal heat flux below the Greenland ice sheet. Very high. They suggested like 15 to 30 times continental background, which is completely crazy. It's like a thermal springs, right? Rather, right? And they suggested that this whole thing is happening because there are volcanoes under the Greenland ice sheet. But why do we have volcanoes in the middle of the Greenland island if it's very ancient lithosphere? It's Archean to Proterozoic, according to what we know, right? So it should be cold and very thick, but we have this. So by chance, I came to a presentation of a colleague who was showing his new seismic tomography of the Arctic. And this is what I saw in this tomography. So it's like at 150 kilometers depth, there is something very hot on the Greenland. So this is negative anomaly in seismic tomography, means it's hot, if simplifying, right? So that really coincided with the areas where they found melting. And then it took us 1 year to unfold the whole story. So this is today the present day location of Iceland. And this is, you know, about Iceland, there is volcanic activity there, right? Due to two reasons. One is because it's mid-ocean ridge. But another one, there is a very hot thing below Iceland, which is called mantle plume. I will define it in the next slides, but it's a very hot material coming from very deep within the earth. And this is why we have volcanic eruptions there. But this thing was 70 million years ago under the west or northern western Greenland due to plate tectonics. So in between, Greenland passed over the Iceland mantle plume. This is where it's 40 million years ago, and we are approaching the current time. So you saw it, right? It's not just me. Yeah, so it looks like this thing is actually connected to Iceland, where we have mantle plume today, and between 80 and 35 million years ago, Greenland passed over this very hot spot, like hot material. Yeah, so it comes all the way from the core mantle boundary, according to what we know today. Yes, and this is from our model, the interpretation of all the data that we have assembled across Greenland about melting, and we managed to reconstruct the geothermal flux that's actually closely coinciding, that is coinciding with the anomaly in seismic tomography. You can see it, I hope. So it's not any close to volcanic activity because, I mean, it's up to 100 milliwatt per square meter. That's, yeah, normal background for active regions, right? Not the crazy numbers that they suggested before, at least. But still, it's enough to melt all of these areas of the ice sheet. Yeah, so this passage of the Greenland lithosphere over the mantle plume left this hot imprint that drives today the melting of the ice sheet, but also some crazy behavior in terms of ice sheet dynamics. I don't want to drag it here because it's too much information. So this is the longest ice stream that exists in Greenland. It originates exactly in the heart of this anomaly. Okay, paleoglaciology. Let's go into this and try to understand what we are doing here. And that's a very big subject of my research. And I'm also leading work packages on numerical modeling on two very big projects, very successful two, one in Antarctica, another one in Central Asia. So a question to you, which ice-free areas had glaciers on Earth in the past? What do you think?
How far?
Yeah, let's focus on the last glacial interglacial period first. I mean, of course, all the planet had glaciers at some point. Great. Yes, but in the past, you mean they still have, right?
There are some places over from 36 degrees south that were covered with ice sheets, but now they won't cover.
Yeah, north of 36. Yeah, maybe it's longer. It's longer than the last glacial interglacial. I mean, yeah.
Central plains of North America.
Yeah, perfect. Very good. Any other places?
Scandinavia?
Oh yeah. What? Perfect. Even Germany in Berlin or like in Potsdam, they have these moraines, right? But yeah, my office in Norway was located basically at the 3 kilometers of ice 20,000 years ago. Okay, these are the reconstructions more or less. They're not very precise here. It's just for the visualization. Yeah, we see the huge changes in the northern hemisphere much more than in the southern. 3 ice sheets merged in, or they grew and merged into one in North America. They covered most of it and also connected to Greenland. And then we had a huge ice sheet also with 3 connecting ice sheets in northern Europe and much bigger glaciations in other mountainous areas, even though we didn't have ice sheets really. These were just bigger glaciers. In the southern hemisphere, we just had 1 extra ice sheet, which is the Patagonian, very small, the smallest of all that we had 21,000 years ago. This is more or less when it was. My team has been working for quite some time with the North American glaciations. Specifically, we take geochronological evidence. We know when the ice sheet was there, when it was retreating. And then we use models to interpret how actually it happened, thanks to which processes, right? We have been working in Central Asia with this big project, CAP, which is Central Asian Paleoglaciology Project, since very long. It started in 2005, so collected huge data sets. And more recently, also with Andres, that was 2 of my PhD students, we have been working on the Patagonian ice sheet. That's more recent and will persist in the future in our research. And one very big focus has been since 2014, and even earlier a bit, on the Antarctic ice sheet. As I mentioned before, we have a very successful project called MAGIC DML. It stands for Mapping, Measuring, and Modeling Antarctic Geomorphology and Ice Change in Droning Modeland, East Antarctic. It's here, right? And we have gone through many expeditions, not me, I'm working on modeling, but our team. They go to Antarctica and they collect data to be able to interpret how the ice sheet looked like in the past. I'll explain a bit how it works, but until now the project gained up to 15 million euro, so it's very, very big, but it has a continuity now, which is called differently. So let's have an overview of what MAGIC DML did. First of all, the logistical support, mapping of where we can collect samples, where we can go. We have our special tanks for moving on the Antarctic ice sheet. They have been developed for MAGIC DML, and we need to map where there are big holes where these tanks can fall, for example, right? With very high resolution of 30 centimeters, we map all of this. And then we do modeling as well to interpret this, so that we select strategic locations for data collection in the field. Then they go to the field, they crack rocks, nunataks, these ones that are sticking from the ice, and they collect data that we can understand when the ice sheet was higher than today. And then these rocks go to geochronology lab in the US to be interpreted in terms of age, right? And then we know, more or less, that's when the ice was higher than today. And then we go again back to the modeling and remote sensing, and we interpret this. Okay, that's simple concept, but this year, 1 month ago, we got the new stage of this project, IQ 2300, approved for full logistical support by Swedish Polar to link past, present, and future of the Antarctic ice sheet until 2300. For 5 expeditions, this year it's still Magic DML, next year it will be already IQ 2300. This is too much. This is too much. You see, 14 work packages. I'm not going to walk through them, but what we want to do, we want to use really expensive equipment to map all the seafloor, to observe ice shelves, processes below ice shelves, right? Then we want to track subglacial hydrology, basically perform geodetic observations of how bedrock is changing, and then also include the paleo component to link all of this and plug it into our models, which are constantly developed, to actually understand this whole system. And thanks to my move to Chile, we gained a different spatial scale. If we look at the Antarctic ice sheet, this is where we worked before. Now we're working in East Antarctica, in the Amundsen Sea sector, and the Larsen ice shelf area. So all 3 of them, to understand different stages of failures that are already going today and will happen in the future in East Antarctica. Okay, that is my invitation to you if you want to join. We have a lot of money and there will be more money because it's 12 countries applying for funding. It's huge. And then from here on, I actually branched again into paleoclimatology. So I moved to Bremen to get teaching experience, but as part of this, I got integrated in a huge nationwide project called PALMOD, focusing on the reconstructions of the entire glacial interglacial cycle with very high complexity Earth system models, fully coupled, and also paleoclimate proxy data. So this is my reconstruction of the North American ice sheets using the in-house Earth system model of Bremen. But just to explain how big this is, this whole project runs for 10 years, it's still running, with 60 postdocs and 40 PhD students in parallel. What they're doing, they're running simulations. One simulation with coupled climate model takes 18 months to complete. So that's just that you understand. And this is what the government of Germany decided to fund. And if you look at this, the results are far from, again, the animation. Okay. Anyway, that's the animation was supposed to show that the coupled simulations are not handling very well the reality. Finally, physical geography. Where did it come from? Right, I got a permanent position in Norway, and then I had to go back to school again and study how to do observational glaciology because my students didn't want to sit in the office and do modeling. So, yeah, that was great, you know. I was thrown like this over the cliff, and the team was learning how to rescue me from the cliff, which was probably 50-story building. And yeah, all of this I had to learn. Safety, the climbing. Can you imagine me, numerical modeler? Yeah. And then in addition to this, I had to learn how to do LiDAR, some GPR, ground penetrating radar, weather stations, cameras. Yeah, trust me, it was not easy. But thanks to that, we got one of the most successful projects I have today, Gothica, funded, and it grew from one master thesis to something quite big today. So originally it was focusing on Europe and Central Asia only, and we wanted to work on how glacier changes impact hydrological systems and people. And there are two aspects to this project. One is on the impacts of glacier changes, like melting, retreating, disappearing, on environment, so natural sciences. And I'm actually approaching to the end, so if you are already falling asleep, it's time to wake up maybe. So basically, we are looking at the recent and long-term glacier and hydrological changes. Then we are developing monitoring systems and prognostic tools for hazards related to those aspects. Some examples of them: glacial lake outburst floods. I don't know if you know this, right? Disappearing rivers in one day or two. The river is just, it goes out of existence. When the glacier collapses, a huge part of the glacier just goes down and collects all the waste on the way and kills a lot of people. This is all what we are working with. And then we are making it into the science fiction. So we are trying to improve future projections of these changes and how these hazard cycles are working and impacting ecosystems. The other one is actually how this all is impacting society. And here we have social sciences. How people are protected from floods, water scarcity, agriculture, hydropower. And then we involve citizens in collecting data, especially at high altitudes, develop early warning systems to warn them that the flood is coming. And then we are also developing adaptation strategies for the impacts that we project into the future on communities and businesses. So, and that becomes very relevant for my new position at SIASA. It's just the overview of what happened. One master thesis. Today we have 15 staff members in Norway only on this project, and then 23 countries are collaborating with us right now. And the methods include, obviously, numerical modeling that was already here in my case, in situ observations, then remote sensing, and machine learning. So I actually went back to that time and linked it here to natural hazards. And then social sciences too. I supervised the two theses on the social science. I'm not an expert in them. I'm just getting an idea about this. Yeah, and that's how I ended up at SIASA. And that's my invitation to a new branch that is developing now through many applications. So Gothic is expanding to the Andes very quickly, and it has a new name. So we are interested in hydrology, ecosystems, and communities, how they are responding to changes in glaciers in alpine environments in general. We are open to any regions on this planet. Yeah, thank you. So that's another invitation.
No, that's really great. Anyone who have questions? Mr. Lundin, please join me.
So, thank you very much, Ian, for your talk. So my question is more about the Gothica project. It's a big umbrella, but this is a project that if you want to get involved, I have to bring my own funding, right? Or you have also funding to run the project.
So, the first thing I did when I moved to SIASA, I started applying for funding. So there will be a lot of funding, we are already getting it. We just got inside information that we got PR. So we also got invited to a new project which is already being implemented. So yeah, we're going to hire a lot.
But it's not Chilean funding. It's
Chile. I need a project PR, regional peak. We have Nuclear Millennium, which was very successful, but we didn't make it to bid, so now we are pushing. and will be a research center, hopefully proposal next year. So we will do a lot of stuff around Baltica. It's my main job at Siasa to rebuild the team because the team is falling apart. They have been alone for a long time. The leader of the team left the country almost 3 years ago. So they were just surviving. Yeah. I mean, it's good to get some fresh blood. But when I arrived, I had very different illusions about the situation because the team is really, really strong. But it's just an illusion right now.
Is it really respond? Yeah, I think it's
So everyone who is ready and willing to join applications is truly welcome, or if you want to work in some other capacity, supervising PhD studies. So we are very open, and it's an open call, right? We are now discussing the submission of nuclear. It's another reason why I'm here.
Yeah, super. Another question regarding Patagonia. How did you construct the model? Did you use some marine observations or?
That's exactly the focus of our paleo studies. I don't know how to go all the way back, but so
it was a few years ago. It was a paper from Davis.
Yeah, exactly.
I used that data.
Yeah, but also there are some even more recent publications that are coming out, more regional, improving, suggesting even that the ice might have extended much more to the north than it was thought before. So we are collecting all this data. In the future, hopefully, we can even connect to the teams working there, right? I have connections already here with some people who are part of the Davis study.
So just to let you know, we are working in a similar project to Antarctica. You know Antarctic, this big GIS data set of Greenland, which is a GIS with all the data available of these regions.
Yeah.
We are doing some more a small scale, of course, but for Patagonia, we are doing because we are more observational geology, so we have a lot of data in that area.
And if you are interested in collaborating, we are very open to enter all our modeling tools and expertise. I think this is a strong collaboration we can have. Like, I'm much less observational person. You saw me, and I was just thrown into this against my will in a way. But
of course, models need better data for parameters.
Absolutely, models are data is science fiction. So the more data there is, the better it is. This is why Patagonia negotiations were not really studied until recently with modeling because it was so scarce. There was almost no constraint. Or even today, we don't have much of constraining data for the altitude of ice, only for the expanse. But this approach of moon attacks hasn't been really slight so far. Maybe there are no locations where we can do that properly, but.
So now there's more data of actually ice thickness, elevation changes, frontal changes.
That's perfect.
So,
you have these data sets.
So we will make it public soon, I think.
Great. So, but we can collaborate on this and perform model simulations. We can make a collaboration on, like, if you are working in a certain region, right? You can refine and
we are working from the 45 latitude. So the Hudson volcano towards so to the all the way 45. So 45.
So from here,
there's MPI around in Patagonia, still a little bit north of Hudson. This is the limit.
Okay.
This is we will collect all the data and should we have a website ufuegopatagonia.org.
Great. Maybe.
How much data will be this compared with Davis, and it's gonna change things maybe, or it's just a complement and stuff?
It's complemented. The data from Davis is into this data set, but also we have ice thickness measurement for iron data. We have frontal changes for all the papers, historical reports, for example.
Right.
We have the GNSS stations because actually this area there's a lot of points that they were measured for estimation, the EIA. What else we have to do in this database?
Do you have-
Climate data as well.
Do you have a modeling team working with you, or you are just focusing right now on?
Yeah, we started because we get a lot of data to, well, I did my PhD in Germany, so we've been working many years in Patagonia. Of course, we are using model, but the data needs to, for this model, you need good data.
Yeah, sure. Yeah, well, you have two PhD students, as I mentioned, both Chileans, both in Europe. So if you want our long-term expertise, or maybe use two different models to do the interpretation, we are ready to do it.
So there's another paper coming out in a couple of weeks in scientific data that we publish is hydroclimatic database for Patagonia that we use it for as a input data for the mass balance models of your modeling.
But hydroclimatic, but with what time?
Present day,
Yeah,
last
yeah,
40 years, so it could be usable for tracking or for validating present simulations.
Yeah, definitely.
Actually, that paper is in our data. It's
Yeah,
from a
that's-
while back.
Yeah. So it's gonna be published, it's gonna be in his database, it's gonna be also on your own GitHub or something.
Great. More data.
So that's easily ingested in a model like yours. So
Yeah,
I have a question, particularly on that, you guys are starting looking at the Patagonia history, particularly the last 21,000 years. And most people, almost everyone, that's Patis, right? That's the reconstruction from Ben Davis.
that sounds good.
Yeah, so the north, it doesn't make sense. So the models don't do anything good, but the observations are really incomplete.
Yeah.
So we are the only group here in the University of Massachusetts that are actually looking at the what is possible to see from Pleistocene, and we are realizing that those north sections is totally wrong. So the problem is that are wrong, you don't know if the models are going well. Right? More like it's basically more like a comment because most people focus on NPI and not SPI. But really, where we don't have data is on the northern section of the ice sheet. That's the big question.
It's just very recently, the people, the team of Glasser, discussing Glasser, they actually questioned this, but it's also published already, I think. That they suggested it was expanding much more to the north. But yeah, there are alternatives, we have to live with them. We changed our strategy, now we're focusing on the actually understanding the reasons why. Okay, let's simplify that. In the whole world, the biggest ice sheets were at around 21,000 years ago. But in Patagonia, according to what we know, it actually happened much earlier during marine exodus stage 3, so maybe 35,000 years ago, it started already retreating. So we're actually looking into these processes now, why might have been within the uncertainties. Because we do have some indications that this might have been a common feature for the southern hemisphere. That means it's much bigger than just this ice sheet. But we are at the beginning of this story now.
So for you, what's the big uncertainty in this area? So what sense the
Patagonia
Patagonia? So no, there is a
the biggest uncertainty, I can tell you, climate models are trash.
yeah.
And that's it. This is the biggest uncertainty. Whatever we do with the ice sheet modeling, we cannot fix these global models that fail to capture any of these orographic barriers, precipitation impacts. It's awful, the quality. So we need downscaling, we need significantly better models for failure.
In this sense, also, what's the state of the art of doing the solid earth response to GIA? Because how important is that process for the outcomes not considering solid Earth response in controlling the uncertainties that you mentioned in the climatic models. At the end, should be something incredible, no? When
You mean
you
in the
couple the
climatic?
atmosphere with the issues with the solid Earth, that's impossible, of course. At
No,
the
I
moment.
mean, it's
We are
possible.
very, it's, yeah, but we are very far from that. But it's going to be important, really, the influence of the solid Earth response in terms of driving the GIA response and controlling at some extent also the interaction relationship with climate, or it's not important?
It depends. I mean, if we are looking specifically at Patagonia, in some areas it will be very important where the ice cover was thicker, obviously. Also, the lithosphere pass relatively thin.
Very
So
thin,
it's
very hot.
very responsive.
Very weak.
Yeah.
Low viscosity and
Yeah, exactly. So it
rapid
will be,
response.
it will be very important in many ways to include it, and we are working on it, as you know. I mean, hopefully that will happen as part of the rest thesis, but we got just got one more person into the team. So one more person into this thing, Frank Irina, my master student. So he will be mainly working on the Antarctic region, but he will continue working on this too. So hopefully as part of this we can include the solid Earth component, because as I showed to you, oh no, that was after that. So our strategic thing here would be to use this huge stuff to develop the coupled model, right? And then transfer it to the region where we might not get as much funding. But if you think about the peninsula and West Antarctic, the region is not so different from what we have here. Because, right, we have volcanic activity there, we have a lot of like really thin lithosphere. So if we manage to develop it as part of this consortium, then we can just transmit it. Maybe we'll get some extra dedicated PhD students to do that, and then we can do it faster.
But to make it more clear, at the moment, the people really do these things in separate stages. No? So they the GIA stuff separated from the climate modeling.
Okay.
In terms of, I mean,
It depends on what do you mean climate, like global models?
I don't know if that's global or not, or if that's those from the so the previous one from
That's
the very old
the
models here in Patagonia that they are coupling atmosphere with the cryosphere, but they are not considering actually the movement of the Earth. No? And we can do it that separated from the influence of the solid Earth, and the problem is now trying to combine this. And,
no, I don't know about, I don't know anything that will be coupling.
It's not, to be honest, working separately.
So what is done first? Like the run climate models, global climate models as part of comparison, or as part of this huge project like we did with paleoclimate, right? So full glacier cycle reconstruction. It's a very coarse model. They have resolution of, in the best case, 2 degrees. 2 per 2 degrees. That's 200 kilometers, right? More than 200 kilometers. One cell, 200 by 200. And this is where we get the solution. It's impossible to deal with Patagonia with this kind of resolution. So they're not coupled usually to the ice models either. So you're just running them, then you run model, cryosphere model. But the cryosphere model, the glacier model usually has at least simplified GIA models as part of it. So if you're making this link from climate to GIA, there is something included.
Yeah.
In the climate models, it doesn't make sense.
Really coarse. Yeah, really coarse, and probably just 1D or perhaps
I mean,
2D.
it's not 1D, it's global, it's very complex.
Yeah, in terms of the changes in the reality of the Earth. It's just.
Yeah, well, if I wanted to make you laugh, I would show, like, we have our white paper in discussion, and we're showing there how ice sheets are represented in the climate models. This is like Tetris, you know. It looks like Tetris. And it has nothing to do with the reality, absolutely.
Well, there are older constructions anyway, so they pull up this 4G, I guess. There are older constructions that are going into the ECNs, and they now have some versions that they can make, for instance, Antarctica and Greenland to evolve in time. but with the resolution that we have available right now, but the work is no, you cannot. Just have a technical question. In which HPC are you running all this? Because I don't know if they're doing it from Chile.
You are talking about
which
tech?
high computer performance, so where are you running these things? In Norway or here? All of them, because you're doing a lot of computing things. I will tell you that we have time to do many things here, we don't have the computer resources to do all of that, I mean, in parallel. So I guess you will still have access to HPC Europe or something?
I have a lot of PhD students in Europe.
Okay.
A lot, I have an army of PhD students in Europe. And all of us, we have access to everything. I'm also in a very good situation, for example, at the newspaper, all my publications for a lot of things. So because it's good, and I still employ them. So I do have access to the supercomputers at NTNU, but also some of my students there in Sweden, in Germany, in the US. So yeah, but CIASA is also quite strong in meteorological stuff. We have quite a good class there as well. Yeah. So to have access to the supercomputing power, you need an army of PhD students.
Exactly.
Yeah.
Great.
So-
Any questions? Preguntas, chicos.
No sé, la pregunta es por computadora.
La pregunta es millones.
Yeah.
Tenemos chicos en su computador.
Sí, por eso, para todos. Ese es el problema. So we have, there is a HPC in Chile, but it's for everyone.
Yeah.
So it's like, the queue is like 5 years.
5 years.
It's I'm just joking, I don't know.
It's like here 1 year, I would say, but you and it's only 1 year, and you don't have the,
So
they're
there's
not
no,
allowed really to make big things. So it's a big machine.
yeah, it's, but everyone uses it, so.
Necesita 5 años, pero
Sí,
Un año.
sí, probablemente. So sometimes when we run things, we might put colleagues somewhere else.
Well, CIASA is also, and they have some connections in Europe where they also run. The climate model that we discussed, it's run in France, for example.
Okay, makes sense.
Yeah. But, I mean, the cluster at CIASA is not really too bad because they make weather forecasts all the time, so it can be used for some purposes, not for this, obviously, this 18 months continuous simulation, right? And then you open it, it's, that.
So last question on my end, so you mentioned you're developing IC models.
Yeah.
What is your starting point? You're developing from scratch, from the primitive equations, you're using another model to modify, you're adding new stuff like erosion or something, glacier erosion?
A bit of loaded question. Okay, so I have several directions to develop. Ice sheet models is one thing, but in the Gothica, there's a glacier, hydrology, like a lot of things are entering that. So these are completely different hierarchies of models. The ice sheet model we have developed so far for MeasureDML is like first component, life scale is Psychopolis. Plus, there is a new model that has been developed in Utrecht by Jorge Bernays, my first PhD student. Yeah. That's specifically for a new Antarctic project. It's called euphemism, very, very powerful stuff, very like hybrid with adaptive grid and stuff like really. Then there is another one component for regional. Like if we're working with regions, we employ very high resolution. Higher complexity, like full stops models, Elma ice, and also to bridge it, we use FOA. It's like more simple but very high resolution. So we have several layers of these models that we're using, and now we are going to couple to the regional ocean model for below ice shelves. This is why Franco, we got a 4-year PhD for him. It's Sweden and Stockholm. And he's going there to develop it further to couple with the ocean. Potentially, we will do some downscaling for the atmosphere. But that's the next stage of development. And then for Gothica, it's a completely different type of models. These are surface energy, really high complexity models with, dynamic MRIs coupled to hydrology, subglacial, interglacial. It's really very complex. Then, of course, coupled to hydrological models of two different complexities: hydropool, which is dynamic hydrology model, and then Kerkas, it's more like to make fast calculations. So these are several hierarchies, and in the Gothica project we also use regional glacier model, which can be run for many ice caps, and LMIs is run for just individual cases. Where we are not yet, it's to simulate the glacial converse flux. This is very complex, but I have one PhD student who is working on a model to do that. Nobody knows how to work it. Yeah, so a lot of works.
And what about glacier erosion?
No, not part of our research yet. It's too much. Maybe we will introduce it in the future, but right now, I don't see how I'm going this way. And for which purposes, for example, which line skills I'm thinking about, like paleo?
Pleistocene.
Yeah.
Divide
It's important, but we have to choose our battles,
No, sure.
Until recently, I had 35 people in my team. I couldn't handle this anymore. Now it's smaller, but now I got additional here. It's Siasa. It was crazy. Yeah. And honestly, I have a full teaching position. I didn't have time to do any research except for weekends and nights.
In Norway. Full teaching.
Yeah, it was supposed to be 47%, but it was full teaching.
Well,
I told you, like, we had Department of Geography, we had 16 human geographers and 2 physical geographers, professors. And we have to pull the entire, social science faculty, like all the teachers of geography, all these, we had no students, 2 of us, and all together became geographers. They all came to us because it's much more fun, we go to the field. So I had 6 master students at the same time, 4 bachelor students, and some human geographers would have 1. Yeah, no, I survived.
so I'm glad you're in Chile.
Yeah, no, I am in.
At least the weather is better. At least it's better.
Everything is better, trust me, and also my family is all food here.
So, well, thank you very much. A round of applause again. Talk about between 10 to 15 people connected.
Yeah.
So that's the number of people who see here is pretty common here.
I don't mind.
For December, especially for today, December. So,
Yeah. Okay. Yeah, that's a good point. Now it's